Okay, today we're going to examine differentiability and how a derivative might fail to exist within the domain of a function. There are four situations. The first one, the function has a corner, a place where the one-sided limits differ. The best example of that would be to take the graph of y equals the absolute value of x. Okay. At x equals 0, we are going to have a corner here. And what happens is the limit as x approaches 0 from the left of our difference quotient is -1, because as we come in from the left, the slopes are -1, the slopes of our tangents, and the limit as x approaches 0 from the right of our difference quotient, f of x minus f of 0 over x minus 0, that is equal to 1 as we move closer to 0 along the right side of the graph. The slopes of the tangents are 1, and since the two one-sided limits, the left side limit and the right side limit, are not equal, that means the two-sided limit does not exist. And the two-sided limit is the derivative, and so therefore the derivative doesn't exist in that situation. Another situation would be where we have a cusp. An example of a cusp would be this particular graph. This happens to be the graph of y equals x raised to the 2/3 power. You can put that into your graphing calculator to check. But in this case, what's happening as we approach 0 from the left, our tangents are approaching -infinity. And then as we approach 0 from the right, the slopes of our tangents, our derivative is approaching +infinity. Again, we're approaching two different things, and therefore our two-sided limit does not exist. Moving on, the next one where there's a vertical tangent, the secant slopes are either approaching +infinity or -infinity. So an example here would be a graph that looks like this. Doesn't necessarily have to be centered at the origin like this one does, but it's going to have this type of a little curve or twist in it. Y equals, oops, I'm sorry. Let's change this. Should be y equals the cube root of x, or x to the 1/3 power. In this case, as we approach from the left, we're going to get tangent slopes that are approaching +infinity. As we approach from the right, our tangent slopes are also approaching +infinity. So for the vertical tangents, both of the one-sided limits are going to approach the same value, but it's infinity, and therefore the two-sided limit doesn't exist. And since the two-sided limit is equal to the derivative doesn't exist. And then the last situation would be a discontinuity. It causes one or both of the one-sided limits to be non-existent. Example of a discontinuity would be here. Obviously, the left-hand limit and the right-hand limit are both the same still. They're 0, but they're not actually equal to f of 0. In this case, both of the two limits happen to be the same number, but the one from the left-hand side, excuse me, this limit does not exist. And we can tell that because of the fact that the point at 0 does not exist there. The limit up above exists, but this particular one does not. Now, from all the points in the domain of f of x equals the absolute value of x minus 2 plus 3, we're going to find those where x is not differentiable. And so what we need to do is perhaps take a look at the curve and see what that curve looks like. Use that to help us find our answer. While f of x equals the absolute value of x minus 2 plus 3, well, it's going to be the absolute value curve shifted 2 to the right and 3 up. So the vertex is there. If we put this into our calculator, we'd end up with the same thing. Remember, for differentiable, we're looking for situations of a corner, a cusp, a vertical tangent, or discontinuity. In this case, we have a corner. And because of that corner, f of x is not differentiable at x equals 2. Everywhere it is differentiable. For example, here at x equals 1, it's definitely differentiable. The limit as we approach from the left of the difference quotient is equal to -1, and the limit as we approach from the right of the difference quotient is -1. Remember, when I say difference quotient, I'm talking about this expression, the expression that we're using for the slope of the secant. Now let's finish off by relating differentiability with continuity. If a function is differentiable at x equals a, then f is continuous at x equals a. So if a function has a derivative at a particular value a within its domain, then it's also continuous at that particular place within its domain. And the ones that we want to be careful of are the ones where we have endpoints. To have a derivative at an endpoint, to have a derivative at the endpoint, to limit it as x approaches that endpoint from either the right or left. It will depend on which endpoint we're looking at to determine which limit we use. For a left endpoint, we're going to use the limit as we approach it from the right. And from a right endpoint, we're going to look at the limit as we approach from the left. And those should be a's instead of zeros. And this is an a. Okay. That limit has to exist, actually be a number. and f of a has to exist. If those two things are true, then it's also going to be continuous at that x equals a. Tomorrow we'll talk some more about derivatives, and we'll see how we can use our calculator to do numerical derivatives. In other words, find the value of derivative for a particular numerical value of x.